Right, so in this video, I'm going to talk to you about our work Nightshade. This is about a data poisoning attack against text-to-image models. This is a joint work with my co-authors, Wenxin, Josephine, and Stanley, as well as my advisors, Heather and Ben. So to start, let's imagine ourselves as a gaming company. They will have a set of very successful characters, and we make most of our revenue directly or indirectly through these characters. Now, fast forward to 2022, a text-to-image models start popping up, and these models enable basically anybody on the internet to be able to replicate our characters. They can also generate or put our characters in arbitrary settings that we may not want them to appear in. They can also take this one step further. They can generate new characters that are very much based off on our existing ones and trying to take a share of this market. Unfortunately, this is not a hypothetical attack that may one day happen to a gaming company. So this type of attack already exists today. Right? Take Pokemon, for example. Right? There are already 3 different websites built around just to mimic or generate fake Pokemon characters. And these are some of the results, and they look very good, but we can clearly see a lot of traits, a lot of pieces that are clearly taken from existing Pokemons that we have. This is also not just a problem for the gaming industry, right? This is the same problem for movie and TV studios. These are fake posters, fake characters. The same problem for animation studios, stock image companies, and even fashion designers. And in fact, it is very challenging today to find, a single piece of content online that is copyrighted, that is profitable, but has not been trained into one of these models. Now the question is, okay, what can we do, right, as a copyright holder? And there seems to be 2 possible solutions as of today. The first solution is, well, we can take legal actions where we can wait for the lawsuit results or regulations. Lots of company or media companies are doing this. And the second option is, well, we can trust that all the AI model trainers will respect robotags, will respect the opt-out list that they put up on their websites. And I also need to explain why these 2 methods are not great, or at least not sufficient to the copyright holders. And so in our work, we look at whether there exists a possible protection method that is proactive and can be leveraged by copyright holders to potentially protect their copyright against this type of AI model training. And the core idea here is, well, we can leverage data poisoning attack. I say we can corrupt a portion of the training set with the images that we put up on the internet. And there is some possibility that a downstream model trained on these data will be corrupted to the point where it will impact its normal performance or normal usage. Another question you may have in your mind is, okay, how is this even possible to poison text-to-image diffusion models? Right? Because we know for a fact that these models are trained on massive amount of data scraped from the internet, right? 400 million for even one of the earlier models that we have. And existing work on data poisoning against classifiers seem to show that we need to control at least 1 to 5% of the entire training sets for a successful attack. And that number just way too expensive in this case. But instead, very surprisingly, in our work, we find that there are 2 characteristics of this training set and the training method that make the poison actually possible. Okay, so let me tell you about these 2 characteristics. The first characteristic is that the training set is very sparse. You do have tons of training data, but when you divide up to specific concepts or specific words, there's only a very small fraction of the entire data sets are related to that words. Right? Take anime, for example, very popular concept. There's only 0.03% of the entire training sets are related. Which means that if we only want to corrupt anime or dragon here, and we don't need to, fight against or overcome all the training data. We just only need to deal with a very small fraction of the data that is in this data set. The second characteristic that makes this poison possible is that clean data that are very noisy, right? They're simply data from the internet, right? They are very low quality in general, um, but also they're not optimized, of course, for the model to learn a specific concept. So if you add these together, it seems that it is possible for us to inject a very concentrated, highly optimized dose of poison data into the training sets. And these poison data may overpower some of these noisy clean data related to some concepts. And the goal finally is what we can corrupt how model generates some of these concepts or a small set of these concepts. Now, let me tell you a little bit about how we're exactly constructing this type of attack. At a very high level, we leverage something called clean label data poisoning attack. I say we start with a piece of clean image and a clean caption from the normal data sets. And we'll use this to generate the poison images. So for example here, right, we have a photo of a dog as a caption and a picture of a dog. What we're going to do is we're going to optimize a perturbation on this dog image that is very small, so it is more or less invisible to our human eyes. And we're going to follow the following optimization function, right? What it does is simply optimize the image such that the poisoned image has very similar feature space representation as a different image, right? So the different image, say, for example, is a cat image on the right. We simply minimize this distance in the feature space of an image extractor of a public diffusion model that we assume the defender has. And at the same time, we want to make sure the perturbation is small, so we penalize the amount of norm of the perturbation to make sure it is more or less invisible to human eyes. At the same time, right, once we perturb the image, we're going to keep the caption exact the same as the original image. Right? So what we're doing here is basically an image that looks like a cat image to the model, but the text of that cat image is actually a photo of a dog. Now, as you expect, when the model trains on several of these data points, the model will start to associate the caption or the word dog with a cat image. Or there will be some existing clean images of dog in the data set, so maybe the model will associate the word dog as a combination of a dog and a cat. I'll show you some example in a second. But in the paper, we also have many different techniques that will make this poison a lot more concentrated, a lot more optimized towards attacking a specific concept. So for example, we have a heuristic on selecting the best text prompts and the best images and targets to use for this poison generation. And for more details, please do take a look at our paper. Now let me show you some results. Okay, so these are before and after images after applying Nightshade. So on top, we have original images we use from the clean data sets. And on the bottom row is the poison images, right? Perturbation added on this image. If you zoom into this picture, you'll see there are some small changes, especially if you look at some of the clear, paints, for example, here on the car. And again, at the same time, we make sure the prompts of these images are still the same as the prompt for the original image. Now, let's just quickly review this. So what's going on here is we're going to feed the model with the poison images. And these images, even though it looks very much correct or the same as the original image to us human, this image actually looks really different to the model. Right? For example, the painting of a dog here looks like a cat image to a diffusion model. And this is what happens if the model will train on some of the poison data. Right, so here are the baseline. These are images generated from a clean model using the prompt on the left. And the clean model we're using our tests is Stable Diffusion XL. It's one of their newest model. And if you prompt the model with a picture of a dog, you'll generate a dog image, a car image, and so on. Now, if you query the model with the exact same prompt, but this time it's a poison model. Right, so the poison model poison from 100 poison samples in the data set to 300 to the data set. And we notice that by the time we have 300 poison samples in the data set, the poison data completely overcome the model's original thinking of the current concept. Right? We'll start generating a cat image when we ask for, okay, generate me a photo of a dog. Start generating a cow image when we ask for a car. or impressionist painting if the user has to generate a cartoon painting. We also find very interesting effects of this attack is, what happens if there are two independent attacks on the same model. We can poison the dog to look like a cat. We can poison the cartoon style image, looks like a impressionist style image, happen on the same model. And then we're gonna query the model, say, generate me a cartoon drawing of a dog. And more interestingly, what happens is the model will start generating a cat image in the impressionist style. Okay, so this shows the model internal understanding of these concepts completely shift to a totally different concept, get replaced by the wrong concept injected by the attacker. Now you may say, okay, this is not that big a problem for the AI company because we can only poison so many different concepts, and the AI company can easily switch out some of these words with similar words, for example. Right? So rather than using a dog because AI company know the dog is poisoned, they use words like puppy or a bigger puppy, for example, to generate dogs. And then this attack won't work anymore. And unfortunately, this is not true. What we find is that by poisoning one specific concept, you not only impact how model generate that specific concept, but also nearby concept or concept related to it. And the reason this happens is because model learns about text in a very embedding semantic space. Right? For example, in that semantic space, dog are very close to puppy, husky, and wolf. So that by poisoning that dog concept, you will have a big impact on how the model understand and generate puppy images, for example. So in this example, we show that by poisoning only dog image, it will significantly impact how model generate wolf, for example, which is not even that similar of two concepts. Moreover, we can take this to one step further is, what happens if many independent concurrent poison attack happen to a single model, right? This is realistic in some sense when there are many there's only a few open source models out there and many attackers can potentially poison the same model, but attacking different concepts. What we find very interesting is that once a poison specific model, there's 100 different type of poison attack to 500 different poison attack. You not only impact how the model generates the concept being poisoned, but also just impact how the model generate images in general. Right? So for example, we poisoned 500 concept. We did not poison the concept of person. The person image will start to look like a random noise, for example. That's completely not the same as our original image, even though we did not poison the person. Right, so in the paper, we also talk about other interesting sites. For example, we look at defenses and countermeasures, and we show that it is very challenging to detect this type of attack. Just because there are the clean data set is fairly noisy, as we talked about before. So any detection method will result in a high false positive rate. It's very easy to hide this poison data in this noisy distribution. Right, finally, please do take a look at the paper. Again, there are more interesting results in there. All right, so I want to quickly mention at the end that we did a very interesting live demo for a TV crew who came to our university, our lab, to look at Nightshade. All right, so what happened there was, they did not tell us about the live demo prior. What happened is on the day they arrived, they gave us a set of images from the reporter that was interviewing us. And they asked us to train a model, fine-tune a model on the images, on his images, right? These are mimicked images generated from the model, then train on clean images belong to this reporter. And then what we did was we applied Nightshade to 30 of his images, and we follow the same process of training the model to produce a poison model. And we asked the poison model the same query to generate images of this reporter. And these are the results. It looks more like a cat image, for example, than the reporter himself. And lastly, I just mentioned that the goal, we released for the source code as well as a software prototype for people to use. And the goal here is to build a form of deterrent. right? We hope Nightshade can act as a deterrent so that now there are some risk for an AI model trainer if they simply go on the internet, take data without any consent. There is some small possibility that the model, rather than generating something correct like this, will start output something goofy or just completely incorrect. And ultimately, we hope Nightshade, as well as related work in the space, can push towards a more healthy future between data owners and model trainers. Right? Maybe become too expensive to just take data without consent, that a model trainer will be more incentivized to license data, to ask for consent on the data they use to train their model. Okay. With this, I'm going to stop here. Please do email us with any questions you have, and or recommend you to take a look at the paper for more additional details.